Right now, without your feeling a thing, tiny particles called muons are passing through your body. A few of them arrive every second, born high in the sky where cosmic rays strike the air, and they fall straight down through you, as if the walls in your bones were not there. A muon is a heavier copy of the electron, and the rulebook of physics says it should behave exactly like an electron in every way except its greater weight. For years now, in a small handful of careful experiments, certain particles have been dying in a way that quietly disagrees with that rule. That is the idea I want to build with you tonight, slowly, one plain step at a time. It is called Lepton flavor universality, the principle that nature's particles come in matched sets that must be treated the same, and there is a faint hint, still only a hint, that one set is being treated differently. If you like slow, honest walks through real physics, take a moment to subscribe. So here is the like question we will follow all the way to the end. When a particle falls apart, does nature really play fair? Strike a match, and it burns down. Leave an apple on the counter and it browns. Everything you can see wears out in its own time, and somewhere underneath all of that ordinary aging sits a stranger, sharper version of the same thing. Deep inside matter, individual particles fall apart too, and when they do not slowly wear down. They change all at once into other particles in a single clean event we call a decay. Picture a smoke detector on your ceiling. Many of them hold a tiny speck of a metal called americium, and that speck is slowly, steadily falling apart, throwing out particles that keep the alarm alert. It has been doing this quietly for years above your head. The speck is not wearing thin the way a tire does. Each atom inside it simply waits, and then, at some unpredictable moment, transforms. Here is the part that takes a moment to sit with. There is no way, even in principle, to know when any single one of those atoms will go. You can watch one for 1,000 years and learn nothing about the exact instant it will decay. What you can know, and know with beautiful precision, is the odds. Take a huge pile of identical particles, and a fixed fraction of them will decay in a fixed stretch of time. That steadiness out of pure randomness is the first strange gift of this world. Think of a big bowl of popcorn kernels heating up. You cannot say which kernel pops next or exactly when, but you know that in the next few seconds a certain share of them will pop, and a little later a certain share of what remains. Particle decay works with that same honest arithmetic. We call the time it takes for half of a batch to go its half-life, and every kind of particle has its own. The comparison to popcorn stops in one important place. A kernel pops because heat builds inside it until the shell gives way, so warmth is the cause, and you could point to it. A decaying particle has nothing building up inside. It is not getting hotter, not straining, not counting down. As far as we can tell, it sits in exactly the same state the whole time, and the moment of its change comes from nothing you could have measured beforehand. The decay is written into the deep rules of the particle itself, not into its history. Now bring this back to your own body. Those muons falling through you from the sky are unstable in just this way. A muon lasts on average about 2/millionths of a second before it falls apart into lighter particles. That sounds like no time at all, and by the standards of your day it is nothing. Yet in the life of a particle moving near the speed of light, 2/millionths of a second is long enough to cross the whole thickness of the atmosphere and reach the ground, which is exactly why so many arrive at your feet. So a decay is the moment we get to watch a particle obey, or possibly disobey, the rules. When a particle falls apart, it has to choose what to become, and how often, and in what proportions. Those proportions are not vague. They are numbers, fixed by the deep laws of physics, and we can measure them by patiently counting millions upon millions of decays and sorting the outcomes. That is where this whole story lives, not in the grand collisions you might picture, but in the quiet bookkeeping of how unstable particles die, and in what happens when the count comes back just slightly off from what the rulebook swore it would be. Before we can see why a small disagreement matters so much, we need to meet the particle that started the trouble, the one nobody asked for. In the 1930s, physicists were reading the sky. Cosmic rays, streams of particles born in distant, violent places in space, were raining down on Earth, and by pushing detectors up mountains and into the upper air, researchers could catch the debris. In 1936, two physicists working in this way, Carl Anderson and Seth Neddermeyer, found tracks left by a particle that did not fit anything on the books. It carried the same electric charge as an electron, but it was much heavier, a couple 100 times the electron's mass. At first, there was hope that this new particle was something theorists had been expecting for other reasons. It was not. It turned out to be a plain, point-like particle, a heavy twin of the electron with no new job to do. The story goes that the physicist Isidore Rabi, hearing about it, asked who ordered that. The line stuck because it captured exactly the feeling. Nature had served up a particle nobody had asked for and nothing seemed to need. We now call that heavy twin the muon. It behaves like an electron in every way we can test, except that it weighs more, and being heavier, it is unstable and falls apart. Give an electron and a muon the same push, the same magnetic field, the same electric pull, and they respond by the same rules. The muon is simply the electron's bigger, short-lived sibling. For a while, the muon sat alone as an oddity. Then the pattern deepened. In the 1970s, a team led by Martin Pearl at the Stanford Laboratory in California found a third member of the family, heavier still, which we call the tau. The tau is the electron's biggest sibling, heavier than the muon by about 17 times, and heavier than the electron by around 3,500 times. It is so heavy that it lives an even shorter life before decaying. So the electron is not one of a kind. It is the lightest of three, and the three of them, electron, muon and tau, form what physicists call the three generations of charged leptons. The word lepton just means one of the light fundamental particles that do not feel the strong nuclear force, and I will give it a plainer handle as we go. Think of leptons as the loners of the particle world, the ones that do not get bound up inside protons and neutrons. Here is the shape of the puzzle. These three particles are, as far as anyone can measure, identical copies of one another, differing only in their mass, same electric charge, same spin, same way of feeling every force. If you could somehow set the mass aside, you could not tell them apart. Nature built the electron, then built it again heavier, then built it a third time heavier still, and then, it seems, stopped at 3. Nobody knows why there are 3. Not 2, not 4, not 17. 3 generations is one of the great unexplained facts sitting in the middle of modern physics, written down and confirmed but never derived from anything deeper. When Rabi asked who ordered the muon, he was really asking a question we still cannot answer. For this story, though, what matters is not why there are 3, but a quieter promise buried in the fact that they seem to be exact copies. If the muon is truly just a heavy electron, and the tau just a heavier one, then whenever nature has a choice to make involving these particles, it should not care which of the 3 it is dealing with, apart from the room their different masses allow. It should treat them even-handedly. That expectation of even-handedness has a name, and it is the rule this entire investigation is built to test. Physicists have a slightly playful word for which of the 3 leptons you're holding. They call it flavor. The electron, the muon, and the tau are 3 flavors of charged lepton, in the same loose way that vanilla, chocolate, and strawberry are 3 flavors of the same kind of thing. The word carries no deep meaning. It is just a label for the generation, a way to say which sibling has shown up. With that word in hand, the rule at the center of this story can be stated in a single plain line. When nature acts on these particles through the weak force, one of the fundamental forces we will meet properly in a moment, it acts on all 3 flavors with exactly the same strength. Electron, muon, tau, it does not matter which. The weak force reaches for each of them with an identical grip. That principle is called Lepton flavor universality, and you can hold it in your head as a simple promise of fairness. The Force treats the three siblings the same. Let me be careful about one honest wrinkle because it matters later. The three leptons do have very different masses, and mass is not something you can ignore. A heavier particle takes more energy to make, and sometimes there is simply not enough room to produce a tau where a muon or an electron would fit. So the outcomes of a decay are not always numerically equal across the three. What the rule insists on is subtler and cleaner than that. Once you account honestly for the different masses, the underlying strength of the force, the part that has nothing to do with weight, is identical for all three. Set the masses aside in the bookkeeping, and fairness is exact. Think of three siblings named in a will, each promised an equal share of what their parent leaves behind. One sibling is tall, one is short, one is somewhere in between. Their heights have nothing to do with the inheritance. The will says equal, and equal is equal, regardless of who grew taller. Lepton flavor universality is that will, written into the laws of physics. The masses are the heights, the force is the inheritance, and it is meant to be split evenly. This is not a soft guideline or a rough tendency. In the deep structure of our best theory, the strength with which the weak force couples to each lepton is set by a single number, one value that appears identically for the electron, the muon, and the tau. The theory does not offer three separate dials that happen to be tuned alike. It offers one dial, shared. That is why the prediction is so sharp, and why any real confirmed departure from it would be so loud. A crack in this rule would not be a small correction to a known number. It would mean the theory is missing something, some new particle or new force that reaches for one flavour more eagerly than the others. The comparison to the will breaks down in a way worth naming. A parent could always choose to be unfair, to favour one child, to rewrite the will. There is a person behind it making choices. Behind Lepton flavor universality, there is no chooser, no preference, only the bare mathematics of how the force is built. For the force to play favourites, the mathematics itself would have to be different from what we wrote down. That is precisely what makes a violation, if it is ever truly confirmed, a discovery rather than a surprise. It would be evidence that our rulebook has a page missing. And so the natural next question is where this rule of fairness actually comes from, and why physicists trust it as much as they do. To answer that, we have to open the rulebook itself, the theory that has passed nearly every test we have thrown at it for half a century, and see where Lepton flavor universality is written down. Every particle we have met so far, and every one still to come, belongs to a single organised picture that physicists spent most of the 20th century assembling. It is called the Standard Model of Particle Physics, and despite the modest name, it is one of the most successful things the human mind has ever built. It is the rulebook. It lists the fundamental pieces of matter, describes the forces that act between them, and tells you, with numbers, how every one of those pieces should behave. The matter in the Standard Model comes in two families. There are the quarks, which clump together to build protons, neutrons, and a whole zoo of heavier particles, and there are the leptons, our loners, including the electron, muon, and tau we have already met. Both families come in the same three generations, that same triple repetition, heavier and heavier, that nobody can explain. Then there are the force carriers, particles whose whole job is to pass a force from one bit of matter to another. Light itself, the photon, carries the electric and magnetic force. A particle called the gluon carries the strong force that holds atomic nuclei together. And two particles called the W and the Z carry the weak force, the one at the heart of decay. Holding it all together is the Higgs particle, found at last in 2012, which gives the others their mass. The reason to take this rulebook so seriously is not that it is elegant, though it is. It is that it works, to a degree that is genuinely hard to overstate. Consider the electron and its response to a magnetic field. Theory predicts that response, an experiment measures it, and the two agree to more than 10 decimal places. That is like two people separately measuring the distance across a whole continent, and coming out matched down to the width of a single human hair. Time and again, across decades of experiments at accelerators around the world, the Standard Model has said what would happen, and it happened. You could picture the Standard Model as a finished map of a country, every road drawn, every town named, checked and rechecked by generations of travellers. When you set out with that map, you expect to find the roads where it says they are, and you do. This is the confidence physicists carry into the laboratory. The map has never seriously misled them, and yet the map has blank edges, and everyone knows it. The Standard Model says nothing about gravity, the force you feel most plainly of all. It offers no explanation for dark matter, the unseen stuff that seems to outweigh everything visible in the universe. It does not tell us why there are 3 generations rather than 1. When it was first written, it even assumed the tiny neutrinos had no mass at all, which later experiments showed was wrong. So the rulebook is spectacularly right about what it covers, and simply silent about a great deal it does not. That combination is exactly what makes physicists restless. A theory that were merely vague could be wrong anywhere, and nobody would be shocked. But the Standard Model is precise. It commits to numbers. So if you can find a single place where its sharp predictions and careful measurements disagree, and if that disagreement holds up, you have found a real edge of the map, a road that leads somewhere the map does not show. That is the prize. Not to prove the Standard Model wrong in some sweeping way, but to find the one honest crack that points toward whatever larger theory lies underneath. Lepton flavor universality is one of the sharpest predictions the rulebook makes. To see why, and to see how a particle decay could ever test it, we need to look closely at the force that governs those decays, the weak force, and the 2 heavy particles that carry it. Of the forces in the rulebook, the weak force is the strange one. The others mostly hold things together. Gravity binds planets, the electric force binds atoms, the strong force binds nuclei. The weak force does something different. It changes things. It is the force that lets one kind of particle turn into another, and without it, the deep transformations at the heart of every decay could not happen at all. The plainest example is the one that keeps the sun shining and makes some atoms radioactive. Inside a neutron, left to itself, the weak force can turn one of its building blocks into a different kind, and the neutron becomes a proton, spitting out an electron and a nearly invisible particle called a neutrino in the process. That is a decay, and it runs on the weak force. The particle actually carrying the force in that moment is one of the 2 we met a moment ago, the W. You can think of the W as the weak force's messenger, the thing that gets passed to make the change happen. Now the W and its partner the Z are both enormously heavy, as fundamental particles go. The W weighs about 80 times as much as a proton, and the Z about 90 times. This heaviness has a direct and important consequence. A messenger that heavy can only be passed across an absurdly tiny distance before it has to vanish again, which means the weak force only reaches across a space far smaller than an atomic nucleus. Its arm is desperately short. Picture 2 people trying to hand each other a note. If the note is light, they can toss it across a room. If the note weighs as much as a boulder, they can only pass it when they are pressed right up against each other, and even then it is a struggle. The weak force is the boulder note. It can act, but only when particles are essentially on top of one another, and even then it acts feebly. That feebleness is why we call it weak, and why the decays it drives can take so long, from tiny fractions of a second to, in some cases, billions of years. There is a second thing the W does that will become the whole game. When it is passed, it does not just nudge a particle, it changes the particle's identity. On the quark side, a W can turn one flavour of quark into another. On the lepton side, a W is always produced alongside a lepton and its matching neutrino. And here we arrive at the exact spot where lepton flavour universality lives. When a W reaches for a lepton, the strength of its grip is set by that single shared number we spoke of before. The W grabs an electron, a muon, and a tau with precisely the same force. the messenger does not care which sibling answers the door. The Italian physicist Enrico Fermi wrote down the first working theory of this force back in the 1930s, before anyone knew the W existed, treating the weak interaction as if it happened at a single point. His picture was later refined into the fuller theory with heavy messengers that we use now, but his instinct held. The weak force was its own thing, with its own fixed strength, and that strength was the same wherever it acted. So the weak force is where fairness among the leptons is written into motion. Every time a particle decays through this force and produces a lepton, the rule of universality is quietly on the line. Count enough of those decays, sort them by which lepton came out, and you are directly testing whether the W truly grabs all three siblings equally. But to build the specific test at the centre of this story, we cannot start from a neutron. We need a heavier, richer particle to fall apart, one built around a special heavy quark whose discovery opened this whole line of inquiry. It is time to meet the bottom quark. Quarks come in 6 kinds, and like the leptons, they fall into 3 generations. The lightest pair, the up and the down, make up almost everything around you, since protons and neutrons are built from them. The next pair, the charm and the strange, are heavier, and the heaviest pair, the top and the bottom, are heavier still. The bottom quark, sometimes called beauty, is the one this story turns on, and it was found in 1977. The discovery happened at Fermilab, the great accelerator laboratory on the prairie west of Chicago, in an experiment led by Leon Lederman. Lederman was a sharp, funny man who later won a share of a Nobel Prize and wrote about physics with a comedian's timing. His team was not looking directly for a lone bottom quark, because you cannot catch a quark on its own. Quarks are never found alone. The strong force binds them so tightly that they always come glued to other quarks. So instead, the team found the bottom quark the way you might discover a hidden animal by its footprints. They found a new, heavier particle whose properties only made sense if it was built from a bottom quark bound to its own antimatter twin. That new particle was named the upsilon. It was a small, tightly held knot of a bottom quark and an anti-bottom quark orbiting each other, and its appearance in the data, a sharp spike at a particular energy, announced that a 5th quark had joined the 4 already known. The bottom quark is roughly 4 to 5 times as heavy as a proton, all packed into something with no size we can measure, a true point as far as any experiment can tell. Here is why the bottom quark, of all the quarks, became the perfect tool. It sits high enough in mass that when it decays, it has many possible ways to fall, including some very rare and delicate ones that turn out to be exquisitely sensitive to new physics. And unlike the very heaviest quark, the top, which falls apart so fast it never even forms a proper bound particle, the bottom quark lives just long enough. A particle containing a bottom quark survives for around 1/trillionth of a second before the weak force takes it apart. 1/trillionth of a second sounds like nothing you could ever use, but remember how fast these particles move. Made in a violent collision, a particle carrying a bottom quark can be flung forward at nearly the speed of light, and in its 1/trillionth of a second of life it travels a few millimeters before decaying. A few millimeters is small, but it is not nothing. It is a distance a modern detector can actually see. The particle is born at the collision point, flies a short measurable gap, and dies, leaving a little kink in the record that says a bottom quark lived and died right here. That tiny gap is a gift. It lets experimenters separate the decays of bottom quark particles from the ordinary chaos of a collision, because most other particles decay right at the collision point or not at all, while the bottom quark's brief flight leaves it standing slightly apart. When physicists talk about beauty in this context, they are pointing at exactly this convenient, catchable, briefly living heavy quark. So the bottom quark gives us a decay rich enough to be interesting and clean enough to be measured. But we still cannot study a bottom quark by itself, since the strong force forbids it to be alone. To put it to work, we have to bundle it with a lighter quark into a particle we can make in great numbers and watch fall apart in great detail. That bundled particle is called a B-meson, and it is the true laboratory of this entire investigation. A meson is one of the simplest things you can build out of quarks. Take a single quark and pair it with a single antiquark, the antimatter counterpart of a quark, and let the strong force bind the two together. That pair is a meson. It is short-lived, because matter and antimatter sitting so close tend to annihilate or decay, but while it lasts, it is a real, coherent particle you can make and study. Bundle a bottom quark with a light antiquark, and you get a B meson. There are a few varieties depending on which light quark you use. Pair the bottom quark with the antimatter version of an up quark and you get one kind, with a down quark another, with a strange quark a heavier cousin that physicists call the B sub S. In every case, the heart of the particle is the same, a bottom quark waiting to decay, wrapped in a light partner that mostly comes along for the ride. When people in this field say B meson, you can picture a bottom quark in a thin coat. The reason B mesons are the laboratory of choice comes down to numbers and cleanliness. In the right machine, you can make them by the billions, and you need billions, because the decays we care about are so rare that in any small batch they would never show up. You also need the products of each decay to be things you can catch and identify, and B meson decays oblige. When the bottom quark inside falls apart, it typically produces a spray of lighter particles that a good detector can track, measure, and add back up, reconstructing what the original B meson was and exactly how it died. Physicists built whole machines for this single purpose, and they gave them a blunt, honest name. They called them B factories. Two of the most important were an experiment called Babar at the Stanford Laboratory in California, and an experiment called Belle in Japan. Each smashed electrons into their antimatter partners, positrons, at just the right energy to produce enormous numbers of B mesons and their antimatter twins, over and over, so the decays could be counted with real statistical weight. Later, the giant LHCb experiment at the Large Hadron Collider in Europe would produce B mesons in a different way and in even greater floods. Think of a crash test program at a car company. To learn how cars fail, you do not study 1,000 different crashes on 1,000 different roads. You build a standard dummy and a standard barrier, and you run the same controlled crash thousands of times so that every difference you see is real and not just noise. The B meson is that standard dummy. Every B meson of a given kind is identical to every other, built to nature's own specification, so when you watch millions of them decay, you can trust that any pattern in the wreckage is telling you something true about the underlying rules, not about some accident of setup. And the crash we most want to watch is a very particular one. We want to catch a B meson in which the bottom quark, as it decays, transforms into a strange quark while throwing off a pair of leptons, either 2 muons or 2 electrons. That specific decay, a bottom quark becoming a strange quark plus a lepton pair, is the cleanest imaginable test of fairness. If the weak interaction truly treats muons and electrons the same, the two versions of this decay should happen in a strict predictable proportion. Count both, take the ratio, and you are reading nature's fairness straight off the page. There is only one problem, and it is a deep and useful one. In the rulebook, a bottom quark is not actually allowed to turn straight into a strange quark in the way you might first imagine. That kind of transformation is forbidden as a single direct step, and the reason it is forbidden is the next piece we need. To see why a bottom quark cannot simply become a strange quark in one step, we have to look again at what the weak force actually does when it changes a quark's flavour. The messenger that changes flavour is the W, and the W carries electric charge. When a W is emitted or absorbed, it hauls a unit of charge away with it, and that forces the quark to change not just its flavour but its charge as well. A down-type quark can turn into an up-type quark, or the reverse, because that shift comes with the change of charge the W demands. Quarks come in two charge categories. The up charm and top carry one kind of charge, a positive 2/3 in the usual units. The down, strange, and bottom carry the other, a negative 1/3. The bottom quark and the strange quark sit in the same category. They carry the very same electric charge. So turning a bottom quark into a strange quark would mean changing flavour without changing charge at all, and that is exactly what the charge W messenger cannot do. It can only make changes that come bundled with a shift in charge. You might think the other messenger could handle it. The Z, after all, is neutral, so it changes no charge. But the Z has a strict rule of its own. When the Z touches a quark, it hands it back completely unchanged. Same flavour, same everything. The Z is like a mirror that reflects a particle back as itself. It never turns a bottom quark into a strange one, so neither messenger will do the job directly. A flavour change with no charge change, which physicists call a flavour-changing neutral current, simply has no single particle in the rulebook that carries it out. Picture a city subway map with two coloured lines. On the red line, every stop changes both your station and your fare zone together. You cannot ride it without your zone changing. On the blue line, the train runs in a perfect loop and never lets you off anywhere new. You end up back where you started. Now suppose you want to reach a station that would keep you in the same fare zone, but move you to a genuinely different stop. Neither line on its own can take you there in a single ride. There is no direct train. That is the bottom quark's predicament. The direct route from bottom to strange, with the charge held fixed, is closed. In the language of the field, this decay is forbidden at what is called tree level, meaning it cannot happen as one clean, simple step. And this is not a minor technicality. It is a designed-in feature of the rulebook, a deliberate silence where a direct process might have been. The consequence is wonderful for anyone hunting new physics. Because the simple route is closed, the bottom quark can only reach the strange quark by a long, roundabout path, a detour so awkward that the decay becomes extremely rare, and rare decays are precious. When a process is common, any small new effect is drowned out by the ordinary bustle. When a process is rare, forced to sneak through a back door, even a faint new contribution can stand out plainly against the quiet. A whisper is easy to hear in a silent room, so the forbidden nature of this decay is not a dead end. It is the reason the decay is worth watching at all. But if the direct route is closed, we are left with an obvious question about how the decay manages to happen even rarely. The answer involves a beautiful trick that the quantum world plays, a way of taking a forbidden path by borrowing, briefly, from nothing. And the story of how physicists first understood that trick begins with 3 names and a quark that had not yet been found. In 1970, 3 physicists sat with a problem that was making the young theory of the weak force look sick. Their names were Sheldon Glashow, John Iliopoulos and Luciano Maiani, and the trouble they faced was that the rulebook, as written at the time, predicted certain flavour-changing neutral currents should happen far more often than experiments showed. Decays of particles called kaons, which involve a strange quark, kept coming out much rarer than the theory said they should. The math and the world disagreed, and the disagreement was large. At that time, only 3 quarks were known, the up, the down, and the strange. Glashow, Iliopoulos, and Maiani made a bold proposal to fix the mismatch. They suggested there must be a 4th quark, not yet discovered, which they called charm, and they showed something elegant about what its presence would do. The contributions from the different quarks to these forbidden decays would very nearly cancel one another out, like 2 waves meeting out of step and flattening. The unwanted flavour-changing neutral currents would not vanish completely, but they would be suppressed down to the tiny rates that experiments actually saw. This cancellation is now called the Jim mechanism, after the initials of the 3 surnames, and it was a genuine prediction with real stakes. If they were right, a 4th quark had to exist. For 4 years, the charm quark remained a theorist's proposal, a piece the math demanded but no one had seen. Then, in November of 1974, it arrived, and it arrived so dramatically that physicists still call the event the November Revolution. 2 teams found it at almost the same moment, one led by Samuel Ting at the Brookhaven Laboratory in New York, the other led by Burton Richter at the Stanford Laboratory in California. Each had discovered a striking new particle, extremely narrow and sharp in the data, which turned out to be a bound state of a charm quark and its antimatter twin. The two groups had names for it, and to this day it carries both, written together as the J/P psi. Ting and Richter shared a Nobel Prize for it within 2 years, an unusually fast honour that captured how completely the discovery settled the matter. The charm quark was real, the gem mechanism was vindicated, and the theory was healthy again. But notice what the mechanism actually does, because it is central to our story. It does not make flavour-changing neutral currents impossible, it makes them rare. The cancellation is nearly perfect, but not quite, and the small leftover is where these decays live. A bottom quark turning into a strange quark, throwing off a lepton pair, is exactly one of these leftover processes, allowed only by the imperfect cancellation, forced to be faint. You can picture the gym mechanism as two people carrying a heavy table through a doorway, each pushing from an opposite side. If they push with perfectly matched force, the table does not move at all. If one pushes slightly harder because of some small difference between them, the table drifts a little. In the quark world, the small difference comes from the quarks having different masses, and that mismatch is what lets a trickle of forbidden decay slip through. The heavier the quarks involved, the larger the leftover, which is one reason processes involving the heavy bottom quark are such useful places to look. So the decay we want to study is rare by design, kept faint by a cancellation that 3 physicists worked out before the crucial quark was even found. That rarity is its value. Now we can finally ask the concrete question we have been circling. If a bottom quark cannot become a strange quark directly, and can only do it through this suppressed back channel, then what does the back channel actually look like? To answer that, we have to watch particles borrow for the briefest instant from empty space itself. Empty space, in quantum physics, is not truly empty. On the smallest scales, over the briefest instants, the vacuum churns with particles that flicker into being and vanish again before they can ever be directly caught. They are called virtual particles, and though the name makes them sound imaginary, their effects are entirely real and measurable. The world runs, in part, on these fleeting borrowings from nothing. The rule that allows them comes from Werner Heisenberg's famous uncertainty principle, which among other things ties energy and time together. Nature will let you borrow a large amount of energy, enough to conjure a heavy particle out of the vacuum, but only if you pay it back almost instantly. Borrow a little, and you may keep it a while. Borrow a lot, and you must return it in a flash. It is a strict lender with a clear rule. The bigger the loan, the shorter the term. This is exactly how a bottom quark reaches a strange quark despite the direct route being closed. It takes out a loan. For an instant, the bottom quark emits a virtual W messenger and briefly becomes a different quark, usually the heavy top quark, then reabsorbs the W and settles down as a strange quark. During that flicker, extra particles appear and disappear, forming a little closed circuit in the diagram we draw. Physicists call that circuit a loop, and they call these processes loop decays. The forbidden transformation happens not as one clean step, but as a quick, borrowed detour through virtual particles that exist only for the instant the loan allows. Think of someone who needs to get from one rooftop to another with no bridge between them. They cannot step straight across. But if they are quick, they can leap onto a trampoline in the alley below, bounce, and land on the far roof, using a path that exists only for the moment of the jump. The loop is that trampoline. It is not a permanent structure. It is a temporary route allowed by the borrowing rules of the quantum world, and it lets the decay complete a journey that looked impossible. Now here is the reason this matters so much for hunting new physics, and it is the whole payoff of this chapter. Any particle that can carry the right properties is allowed to appear inside that loop, even particles we have never discovered, as long as it pays back its energy loan in time. The heavier a particle is, the larger the loan it represents, and the more fleeting its appearance, but it can still leave a fingerprint on how often the decay happens and on the details of what comes out. So a decay that proceeds through a loop is quietly sensitive to the entire catalogue of particles that could exist, including ones far too heavy to ever make directly in our machines. This is a genuinely powerful idea, so let me put it plainly. To discover a new particle the ordinary way, you usually have to produce it, which means you need enough energy to bring its full mass into being. That sets a hard ceiling on what any machine can reach. But a virtual particle in a loop does not need to be fully produced. It only needs to flicker. Through that flicker, a particle many times too heavy to create directly can still tilt the odds of a decay by a measurable amount. The rare loop decay becomes a kind of remote sensor, feeling for masses far beyond the direct reach of the collider. That is why the decay of a bottom quark to a strange quark and a lepton pair is watched so closely. It runs entirely through a loop, and the loop is open to influence from the unknown. Physicists even gave the particular shape of this loop diagram a memorable name, one born from a late-night bet, and that name and its picture are worth a short stop of their own. The diagrams physicists draw to picture particle interactions have an inventor's name attached, Richard Feynman, and they are called Feynman diagrams. Each line is a particle, each junction a place where particles meet and transform. The loop decay of a bottom quark has its own particular Feynman diagram, and that diagram carries one of the most charming names in all of physics. It is called a penguin diagram. The name has a real and slightly ridiculous origin. In the 1970s, a young theorist named John Ellis was in a pub with colleagues, and a bet was made over a game of darts. Ellis lost, and the price of losing was that he had to find a way to work the word penguin into his next research paper, whether it fit or not. For a while, he had no idea how he would manage it. Then, while thinking about exactly this kind of loop diagram, he came to see that if you drew it a certain way, with the loop at the top and the lines trailing down, it looked a little like a penguin standing upright. The word went into the paper, the name stuck, and physicists have been drawing penguins ever since. Behind the whimsical name sits a precise picture. In a penguin diagram, the bottom quark emits a virtual W and momentarily becomes a heavier quark, just as we described, forming the loop. But then, from that loop, another messenger is thrown off, either a photon or a Z, and that messenger converts into the pair of leptons we want to count, a muon and an anti-muon, or an electron and its antimatter twin. So the full story of the decay is written into one diagram. A bottom quark climbs into a loop, transforms and returns as a strange quark, and along the way flings out a lepton pair. The strange quark stays inside the B mesons wreckage, and the two leptons fly out where a detector can catch them and carry the signal to us. This is the decay at the centre of everything we are building. When you hear that physicists are studying a bottom quark going to a strange quark with two leptons, you can now picture the actual event. A rare loop, a penguin standing in the diagram, a whisper of a decay slipping through the near-perfect cancellation the gym mechanism imposes, carrying out into the world a pair of leptons whose identities we get to tally. The reason to care about which leptons come out is the rule of fair play. The penguin can throw off a muon pair or an electron pair, and lepton flavor Universality insists it should choose between them in a fixed known proportion once the small mass differences are accounted for. The messenger that makes the leptons, whether photon or Z, grabs muons and electrons with the same strength. So if you patiently collect these penguin decays and sort them by which lepton pair came out, and if the proportion comes back wrong, you have caught the weak force apparently breaking its own rule, in a process so rare and so clean that a small new particle hiding in the loop could plausibly be the culprit. There is a lovely honesty to the fact that one of the sharpest tests of the rulebook rides on a diagram named after a lost bet. It reminds you that physics is done by people, in pubs and offices, with darts and jokes, and that the grand machinery of nature gets probed with tools that have silly names and serious jobs. Behind the smile is real, careful work, carried out by thousands of people over decades. The penguin is a joke that turned into one of the most watched processes in particle physics. Now we can ask the question that makes this whole effort worthwhile. Of all the ways to look for cracks in the rulebook, Why do physicists put so much faith in these rare penguin decays in particular? What is it about the rare ones that makes them the sharpest window we have? There are two great strategies for finding new particles, and they are almost opposites. The first is the one everyone pictures. You build the most powerful collider you can, smash particles together at the highest energy you can reach, and try to create something new directly, bringing its full mass into being out of the raw energy of the crash. This is the energy frontier, and it is how the W, the Z, the top quark, and the Higgs were all found. Its limit is blunt and physical. You can only make a particle if you have enough energy for its mass, so there is always a ceiling, and beyond that ceiling you are blind. The second strategy is quieter, and in its own way, more cunning. Instead of making a new particle, you look for its influence. You find some process the rulebook predicts with great precision, ideally a rare one, and you measure it with enormous care. If a new particle exists, even one far too heavy to ever create directly, it can reach into that process through a virtual loop and nudge the outcome away from the prediction. You never see the particle, you see its footprint. This is often called the intensity frontier, because it relies on collecting a staggering intensity of events rather than a staggering energy per event. Rare decays are the natural home of this second strategy, and the reason is the quiet room principle we met earlier. In a loud, common process, a small new effect is lost in the noise. In a rare, suppressed process, that same small effect can be a large fraction of the whole, standing out clearly. The bottom to strange penguin decay is suppressed to a whisper by the Jim cancellation, which makes it one of the quietest rooms in all of particle physics, and therefore one of the best places to hear something new. The track record of this indirect approach is genuinely impressive, and it is the part of the story that popular tellings often skip. The Jim mechanism itself was an indirect argument, reasoning from the rarity of certain kaon decays to the existence of a whole new quark, and it was right. A few years later, two physicists in Japan, Makoto Kobayashi and Toshihide Masukawa, went further. Studying a subtle asymmetry between matter and antimatter, they realized the two known generations of quarks could not account for it, and that a third generation, unseen at the time, was required. They wrote this down in 1973, when the bottom and top quarks were still years from discovery. Both were eventually found exactly as the argument demanded, and Kobayashi and Masukawa shared a Nobel Prize decades later, in 2008. This is worth sitting with. Twice physicists reasoned from careful measurements of rare or subtle processes to the existence of particles nobody had seen, and twice the particles turned up. The indirect frontiers predicted new pieces of the universe before the direct machines could reach them. It builds on an earlier insight from Nicola Cabibbo, who first understood that quarks of different generations mix into one another in the weak force, a mixing that later grew into the full framework Kobayashi and Masukawa completed. So when physicists stake years of work on a rare penguin decay, they are betting on a strategy with a strong history. They are saying that if there is a new particle hiding beyond the reach of our colliders, one of the surest ways to feel its presence is to measure a suppressed decay so precisely that its faint touch cannot hide. The rare ones matter because they are sensitive, they are clean, and they have delivered before, all of which brings us at last to the specific measurement that set this whole modern episode in motion. It is a simple idea, almost arithmetic in its plainness. You count two kinds of decay, and you take their ratio. The measurement is called R of K, and once you strip away the notation, it is almost childishly simple. Take the rare penguin decay in which a B meson falls apart into a lighter particle called a kaon, which carries the strange quark plus a pair of leptons. This decay can produce a muon pair or an electron pair. Count how often it produces muons. Count how often it produces electrons. Divide the first by the second. That ratio is R of K. The K stands for the kaon that comes out. If Lepton flavor universality holds, this ratio has a prediction so clean it is almost unfair. The penguin's messenger grabs muons and electrons with the same strength, so the decay should produce them in nearly equal numbers, and R of k should sit extremely close to 1. The only reason it is not exactly 1 is the small difference in mass between the muon and the electron, which is well understood and easily accounted for. After that tiny correction, the rulebook predicts R of k equal to 1 to within a fraction of a percent. Few predictions in physics are this sharp. The sharpness comes from a beautiful feature of taking a ratio, and it is worth understanding because it is the whole reason this measurement is trusted. The decay of a B meson is a messy business in one respect. The quarks inside are bound by the strong force, and the strong force is fiendishly hard to calculate precisely. That messy, hard to compute binding physics affects how often the decay happens. But here is the saving grace. It affects the muon version and the electron version in exactly the same way. The strong force does not know or care which lepton pair will come out at the end. So when you divide the muon rate by the electron rate, all of that difficult strong force messiness cancels top and bottom and drops out of the answer entirely. Picture 2 bakers following the same complicated bread recipe, with all its finicky steps and hard to judge timings. The only difference between them is that one sprinkles muon salt on top and the other sprinkles electron salt, and the two salts are supposed to behave identically. If you want to know whether the two salts really are the same, you do not need to master the impossibly complex bread recipe. You just compare the two finished loaves. Whatever went right or wrong in the baking happened equally to both, so any real difference between the loaves must come from the salt. The ratio throws away the hard part and keeps only the question you actually care about. That is why R of k is such a powerful test. It converts a question tangled up in the hardest calculation in the field, the behaviour of the strong force, into a clean comparison where all that difficulty cancels. Whatever value the strong force contributes, it contributes to both muons and electrons alike, and division erases it. What remains is a nearly pure measurement of fairness. If R of k comes back at 1, the weak force is treating muons and electrons the same, and the rulebook stands. If it comes back clearly below 1 or above 1, and if that result holds up, then muons and electrons are not being treated the same, and something outside the rulebook is reaching into the decay. So the plan is set, and it is honest and clean. Produce vast numbers of these B meson decays, sort them by whether a muon pair or an electron pair came out, count each carefully, take the ratio, compare it to 1. Any real gap is a message from beyond the standard model. The trouble is that these decays are rare. The leptons must be caught and correctly identified among a storm of other particles, and telling a muon from an electron cleanly is harder than it sounds. To do all of this at the scale required took one of the most specialised machines ever built for the purpose, sitting in a tunnel beneath the border of France and Switzerland. Beneath the countryside on the border between France and Switzerland runs a circular tunnel 27 kilometres around, home to the Large Hadron Collider, the most powerful particle accelerator ever built. It sends 2 beams of protons racing in opposite directions at very nearly the speed of light, and steers them into head-on collisions at 4 points around the ring. At each of those points sits a giant detector to record the debris. One of them, built specifically for the physics of this story, is called LHCb, where the small b stands for beauty, the other name for the bottom quark. LHCb was designed with the bottom quark's habits in mind. When protons collide at these energies and make bottom quarks, those quarks tend to fly forward, close to the direction of the original beams, rather than spraying out sideways. So unlike the other big detectors, which wrap around the collision point like a barrel, LHCb is built like a series of walls stacked one behind another, reaching forward to catch the particles streaming down the beamline. It is a machine shaped to the way beauty flies. Its first crucial job is to see the tiny gap we spoke of earlier, the few millimetres a B meson travels before it decays. LHCb has an exquisitely precise detector right around the collision point, able to pinpoint where each track begins to a fraction of the width of a human hair. With it, physicists can spot the little displaced knot where a B meson lived its trillionth of a second and then fell apart, separating those decays from the ordinary rush of the collision. The harder job for this particular measurement is telling a muon from an electron. The two are both leptons, both charged, and at first glance in a detector they can look similar. But they betray themselves differently. An electron is light, and when it plows through dense material it sheds its energy quickly in a shower that a device called a calorimeter can measure. A muon is heavier and more penetrating. It punches through layers of iron that would stop almost anything else, and dedicated muon chambers on the far outside of the detector register its passage, so LHCb identifies each lepton by how it behaves, catching electrons in the calorimeter and muons in the outer chambers. This difference is also the measurement's greatest headache, and it is worth being honest about. Because electrons and muons are detected by different systems with different quirks, the machine catches them with different efficiencies. Electrons in particular are trickier. They can radiate away some of their energy before they are measured, smearing the signal. To take a clean ratio of muon events to electron events, the experimenters must understand these differences with extraordinary care, correcting for every way the detector treats the two leptons unequally. If they get that correction even slightly wrong, they could manufacture a false difference or hide a real one. Much of the years-long effort behind R of K is precisely this painstaking calibration. Behind the machine stands a collaboration of well over 1,000 scientists and engineers from many countries, working together for years on a single set of measurements. This is not a lone genius at a chalkboard. It is a vast, coordinated human effort, with people devoted to the vertex detector, others to the calorimeter, others to the muon chambers, and still others to the mountains of data analysis, all of it cross-checked and argued over before any number is allowed out the door. And out the door, over the past decade or so, came a series of results that made this quiet corner of physics suddenly loud. When LHCb first measured R of K and its close relatives, the numbers did not land neatly on 1. They came in low, as if muons were appearing less often than the electrons, as if the weak force were ever so slightly playing favourites. That is the first crack, and it is where the excitement began. The first hints did not arrive all at once, and none of them, on its own, was overwhelming. They accumulated, one careful measurement after another, over several years in the 2010s. LHCb measured R of K, the muon to electron ratio in the decay with a chion, and found it sitting below 1. It measured a close relative called R of K star, using a slightly different outgoing particle, and again the value came in low. Other related measurements of decays involving muon pairs told a similar tale. The size of the shortfall was consistent and suggestive. Where the rulebook predicted a ratio of essentially 1, the measurements kept landing somewhat under it, as though muon pairs were being produced a little less often than electron pairs, by something like a fifth or a quarter. No single result was large enough to shout about, but they pointed the same way, again and again, and in physics a chorus of small consistent hints can feel more compelling than one loud outlier, because it is harder to explain away as a fluke in a single measurement. What made the physicists lean in was not just that the numbers were low, but that a new particle could explain them so neatly. Imagine some undiscovered particle that reaches into the penguin loop and couples more strongly to muons than to electrons, or that adds a new path available to muons alone. Such a particle would pull the muon rate down or up relative to the electron rate, shifting R of K away from 1 in exactly the manner observed. 2 leading candidates fit the bill, and we will meet them properly soon. One is a particle called a leptoquark, the other a heavy cousin of the Z that physicists call a Z prime. Either could, in principle, be the hand tipping the scale. There was a genuine mood in the field during those years, and it even had a light-hearted label. On social media and in seminar rooms, physicists described themselves as cautiously excited, sometimes writing it as a single hashtag, a way of saying they were hopeful but had been burned before. Particle physics is full of promising bumps that melt away with more data, and everyone knew it. So the excitement came wrapped in caution, a held breath rather than a cheer. Part of that caution came from history. The field has a long memory of anomalies that appeared, drew crowds, and then quietly vanished as the statistics improved. Physicists sometimes joke, a little ruefully, that the universe keeps sending them plain confirmations of the standard model when they were hoping for something new. So even as the R of K results kept coming in low, the seasoned researchers refused to celebrate. They wanted more data, more decays, tighter error bars, and above all they wanted to see whether the effect would grow sharper or fade as the counting continued. Because that is the crux with any hint like this. A measurement is never a single clean number. It comes with an uncertainty, a range that reflects how many events were counted and how well the detector was understood. A ratio sitting below 1 means little if its uncertainty is wide enough to comfortably include 1. It means a great deal if the uncertainty is narrow and 1 lies well outside it. The whole weight of an anomaly rests on this comparison between how far the measurement strays from the prediction and how large its uncertainty is. Physicists have a precise way of talking about that comparison, a single measure of how surprised they should be. They speak of sigma and of a strict threshold that a result must cross before anyone is allowed to call it a discovery. Understanding what sigma means and why the bar is set so high is the key to reading this entire story honestly, and to knowing why cautious excitement is not the same as proof. When a measurement disagrees with a prediction, physicists need a way to say how seriously to take the gap, and they express it in units called sigma. 1 sigma is the natural size of the expected wobble. The amount a result might stray from the true value just from the ordinary randomness of counting a finite number of events. A result that sits 1 sigma away from the prediction is nothing. You would expect that much scatter all the time. The question is always how many sigma away a result lands, because that tells you how unlikely it would be to see such a gap by pure chance. The scale climbs steeply. A gap of 3 sigma means that, if the rulebook were perfectly correct, you would see a fluctuation this large only about once in every 700 tries. Physicists call 3 sigma evidence, a level that earns attention but not belief. A gap of 5 sigma is a different animal entirely. A 5 sigma fluke would happen only about once in 3.5 million tries. That is the threshold the field has agreed to call a discovery, and only when a result crosses it do physicists allow themselves to say that something new has truly been found. You can feel the logic with a coin. Suppose you suspect a coin is weighted toward heads. Flip it 10 times and get 7 heads, and you have learned almost nothing. 7 out of 10 happens easily with a fair coin. Flip it 1,000 times and get 700 heads, and now the imbalance is far outside anything a fair coin would plausibly produce, and you can say with real confidence that the coin is rigged. The number of heads did not change in spirit, but the number of flips did, and with it your certainty. Sigma is the physicist's careful bookkeeping of exactly that, how far the result strays measured against how much it could have strayed by luck alone. The reason the bar is set so punishingly high, at 5 sigma rather than 3, is hard-won caution. Physicists run enormous numbers of measurements, and if you make enough of them, a few will wander far from expectation just by chance, the way that in a large enough crowd someone will win the lottery, even though no individual is likely to. This is sometimes called the look elsewhere effect. The more places you look, the more likely you are to find an accidental bump somewhere. History is littered with 3 sigma anomalies that drew excitement and then dissolved when more data arrived, and the fluctuation regressed toward the prediction. The field learned, through repeated disappointment, to demand a great deal before believing. Against that backdrop, the R of K hints were suggestive but modest. Each individual measurement sat around 2 to 3 sigma away from 1, in the zone of interesting evidence, well short of the 5 sigma line a discovery demands. What made them tantalizing was not any single result's strength, but their agreement. Several independent measurements, all leaning the same way, all a bit below the prediction, all telling a consistent story. A cluster of 2 and 3 sigma effects pointing in one direction is the kind of thing that could be the first glimpse of a discovery, or could be a run of ordinary flukes that happened to align. From the numbers alone in those years, you honestly could not yet tell. This is why the calm, cautious tone in the field was the correct one, and why this story cannot be told as a simple march toward triumph. An anomaly is a promise that must be kept or broken by more evidence. Some are kept, many are broken. The only way to know is to gather more data and to look at the same physics from as many different angles as possible to see whether the whole picture holds together or falls apart. And there were other angles. The muon to electron ratio was only one way the bottom quark's decays seemed to be misbehaving. There was also the precise shape of the decay itself, the pattern of directions in which the particles flew, and that shape carried an anomaly of its own. Every decay has a shape. When a B meson falls apart into a kaon-like particle and a pair of leptons, the products do not fly out in random directions. They come out with a preference, a pattern of angles set by the deep quantum rules of how the decay unfolds. Measure enough decays, and that pattern emerges from the data like a fingerprint, and the rulebook predicts the fingerprint in fine detail. One particular decay, in which a B meson produces a particle called a K star along with a muon pair, offers an especially rich pattern to study, because the K star itself immediately decays and leaves extra tracks whose angles can be measured. From all those angles, physicists build a set of quantities that capture different features of the decay's shape. Most are ordinary, but one of them, given the plain-looking name P5', turned out to be a place where measurement and prediction parted ways. To picture what an angular quantity captures, imagine watching many identical fireworks burst and carefully recording the directions the sparks tend to fly. If the bursts are all truly identical, the spray of sparks will follow a fixed statistical pattern. More sparks here, fewer there, and that pattern encodes the physics of the explosion. P5' is one number distilled from exactly that kind of directional pattern in the muon decay, a single summary of how the particles prefer to arrange themselves as they leave. When LHCb measured P5' across the range of energies the muon pair could carry, most of it matched the prediction cleanly. But in one band, the measured value drifted away from what the rulebook said it should be, by around 3 sigma. It was another crack, in a completely different quantity from R of k, arrived at through a completely different kind of measurement. Where R of k compared muons to electrons, this looked only at muons, and studied not how many there were but which way they flew. What made this exciting was the possibility that the two anomalies were connected. Suppose there really is some new particle nudging the muon decays. It would not only change how often muons appear, shifting R of k, it would also subtly reshape the decay, tilting the angular pattern and moving P5'. So here were two independent measurements, one about counting, one about shape, both misbehaving, and both potentially explained by the very same underlying cause. That coherence is what turned a scattering of odd numbers into something that felt, to many physicists, like a pattern rather than a coincidence. But I have to be honest about a shadow over the P5' result, because it is central to the whole story, and popular tellings often leave it out. Unlike the clean ratio R of k, the prediction for P5' does not have all the messy strong force physics cancel away. It depends on hard to calculate effects involving the strong force, in particular the behaviour of charm quarks flickering through the decay. Those effects are genuinely difficult to pin down, and reasonable physicists disagree about how large they might be. If they are larger than assumed, they could mimic the deviation entirely, with no new particle required. The anomaly in P5' might be a message from beyond the rulebook, or it might be a gap in our ability to calculate what the rulebook itself predicts. This is the recurring tension of the entire subject, and it will return again and again. Some of these measurements, like R of k, are clean, with the hard physics divided away, so a deviation would be hard to blame on calculation. Others, like P5', are sensitive but muddier, entangled with the parts of the theory we compute least well. A truly convincing case for new physics would need the clean measurements and the muddy ones to agree, telling one consistent story that the messy calculations could not fake. There was a third strand to that story, quieter than the shape and simpler than the ratio. It was simply that certain muon decays were happening less often than they should. Alongside the ratios and the angles sat a planar observation, almost humble by comparison. For a whole family of decays in which a bottom quark turns into a strange quark and throws off a muon pair, the sheer rate, how often the decay happens at all, kept coming in lower than the rulebook predicted. Not the ratio of muons to electrons, just the outright number of muon decays measured against the theory's expectation. Over and over, across several different decays, the muon rates ran low. There was the decay of a B meson into a kaon and 2 muons. There was the decay into a K star and 2 muons. There was a decay of the heavier B sub S meson into a particle called a phi and 2 muons. In each case, physicists counted how often the decay occurred, compared it to the predicted rate, and found the measurements sitting somewhat under the line. The gaps were modest, each one on its own no more than a couple of sigma, but the direction was stubbornly consistent. Muon decays were simply happening a little less than they were supposed to. You can think of it like a bus route that is supposed to run a fixed number of times a day, according to the official timetable. On any single day, buses run late or early or get missed, and you would not read much into one day's tally. But if you count for months and the buses consistently come fewer times than the timetable promises, always a little short, never a little over, you begin to suspect the timetable itself is wrong, or that something is quietly removing buses from the schedule. The consistency across many days is what turns a shrug into a suspicion. Now here is why these rate measurements mattered so much in combination with the others. Suppose you take seriously the idea of some new particle that couples to muons and reaches into these decays. Such a particle could reduce the muon decay rate, pulling all these numbers down together, and it would do so in a way that connects naturally to the other anomalies. The low rates, the shifted P5', and the below 1R of K could all, in principle, be different faces of a single new effect touching muons. 3 separate kinds of measurement, pointing at the same suspect. But the same honest caveat that shadowed P5' shadows these rates too, and I will not skip past it. The predicted rate of these decays depends on the hard, strong force physics that does not cancel when you look at an absolute number rather than a ratio. Calculating how often a B meson decays into a kaon and 2 muons means wrestling with how the quarks are bound inside, and that calculation carries real uncertainty. So a rate that comes in low might signal new physics, or might mean the prediction was a touch too high because the strong force estimate was off. The clean escape that R of K enjoys, where the messy physics divides away, is not available here. This is the landscape as it stood at the height of the excitement. Not one anomaly, but a cluster of them, in ratios, in shapes and in rates, all involving bottom quarks decaying to strange quarks with muons, and all leaning the same direction. Some of the cluster was clean, some of it was muddy, but the muddy parts and the clean parts agreed with each other, and that agreement was the real source of hope. The obvious question was whether all these scattered hints could be tied together by a single number, one adjustment to the rulebook that would pull every one of them into line at once. Remarkably, when theorists tried exactly that, the answer looked like yes. When you have many separate measurements all disagreeing with a theory in small ways, there is a powerful thing you can do. You can ask whether a single change to the theory would fix all of them at the same time. If each anomaly needs its own separate fudge, the pattern is probably just noise, a collection of unrelated flukes. But if one clean adjustment lines them all up together, that is the signature of a real underlying cause. Physicists call this exercise a global fit, and it became the beating heart of the case for new physics in these decays. The way it works is to imagine the rulebook's description of the bottom to strange decay as having a set of dials, each controlling the strength of a particular way the decay can proceed. In the standard model, those dials are set to specific values that the theory calculates. The global fit asks a simple question. If you were allowed to turn the dials away from their standard model settings, is there some new setting that fits all the data, the ratios and the shapes and the rates, better than the standard model does? And if so, which dial needs turning, and by how much? The answer that emerged was striking in its simplicity. Taking dozens of measurements together, from different decays and different experiments, theorists found that turning a single dial away from its predicted value improved the agreement with all of them at once. One coherent shift in one particular direction pulled the low R of K, the drifting P5', and the below prediction muon rates simultaneously toward the data. The measurements were not each demanding their own separate story. They were, to a remarkable degree, demanding the same story. Think of a doctor faced with a patient reporting a scatter of complaints, fatigue, a strange rash, aching joints, a low fever. Each symptom alone could mean 100 things. But if a single underlying condition explains every one of them together, that diagnosis becomes far more compelling than any list of separate coincidences. The global fit was that unifying diagnosis. It said these disparate symptoms in the data might all flow from one cause, one modification to how muons interact in these decays. And the strength of that combined preference was, at its peak, genuinely arresting. Where each individual anomaly hovered around 2 or 3 sigma, the global fit, by pooling all the information, reached considerably higher, into the range that would ordinarily count as strong evidence. Pooling works because independent hints reinforce one another. 3 separate coins, each slightly favouring heads, become, together, a much stronger case for a rigged mint than any one coin alone. The fit was, in effect, hearing all the small consistent whispers as a single clearer voice. This was the high watermark of the excitement. For a stretch of years it looked as though a coherent picture was assembling itself out of the data, one new effect touching muons, showing up cleanly in ratios and messily in shapes and rates, all consistent, all pointing to the same shift in the same dial. Physicists began seriously asking not whether there was new physics, but what kind of particle would turn that particular dial in that particular way. But to understand what the fit was really saying, and to judge how much to trust it, we need to look closely at those dials themselves. They are not vague metaphors. They are precise quantities with a name and a meaning, and understanding them is the key to translating a shift in the data into a statement about a possible new particle. The dials have a name. They are called Wilson coefficients, after the physicist Kenneth Wilson, and they come from a way of describing physics that is one of the most useful tricks in the whole field. The idea is that when you are studying processes at some modest energy, you do not need to know every detail of what happens at much higher energies. You can bundle all those high-energy details into a handful of numbers that describe their net effect on the low-energy world. Those numbers are the Wilson coefficients. Here is the plain version. Suppose there is some very heavy new particle, far too heavy to make directly, that influences the bottom to strange decay through a virtual loop. You do not have to track that particle in full to feel its effect. Its entire contribution, whatever it is, shows up as a shift in one or more of these coefficients. So the Wilson coefficients act as a summary, a compression of all possible high-energy physics into a small set of dials that govern the decay you can actually measure. Turn a dial, and you're describing the combined effect of whatever heavy physics lies above without needing to name it yet. Each coefficient corresponds to a particular way the decay can happen, a particular structure in how the particles couple. One of them, labelled with the number 9 in the field's bookkeeping, governs a specific way the muon pair couples to the rest of the decay. And it was precisely this coefficient, the 9th, that the global fit wanted to move. When theorists let that one dial shift away from its standard model value by a certain amount, the whole scatter of anomalies fell into better alignment. The data seemed to be calling for a specific nameable adjustment to a specific nameable dial. The beauty of this framework is that it separates 2 questions that are easy to confuse. The first question is what the data want. expressed purely as a shift in the dials, with no assumption about what causes it. The second question is what physical particle could produce that shift. The Wilson coefficients let you answer the first cleanly, model by model be damned, and only then move on to the second. The data spoke in the language of the dials, and the message was consistent. Turn the ninth coefficient, and much of the tension eases. You might picture the Wilson coefficients as the settings on an old radio, one knob for volume, one for tone, one for balance. You do not need to understand the circuitry inside to notice that the sound is wrong, and to work out which knob, turned which way, would fix it. The Global Fit did exactly that. It listened to the data and concluded that one particular knob was set wrong, and it even said by how much and in which direction it needed to turn. But, and here is the caution that the honest version of this story must keep returning to, a knob turning is not the same as knowing what hand is turning it. A shift in the ninth coefficient could come from a genuine new particle reaching into the loop. Or, troublingly, it could be mimicked by those hard-to-calculate strong force effects we keep meeting, the charm quarks flickering through the decay, which happen to influence the very same coefficient. The dial can be moved by new physics or by an underestimate of ordinary, messy, known physics, and from the shift alone you cannot always tell which. Still, if you set that worry aside for a moment and take the shift at face value as a real new effect, the natural next step is to ask what could cause it. What kind of particle, added to the rulebook, would turn the ninth dial in just this way? Two candidates rose to the top, and the first of them is a genuinely strange and appealing beast. The first candidate is called a leptoquark, and its name tells you exactly what makes it so unusual. In the standard model, quarks and leptons live in separate worlds. Quarks feel the strong force and clump into protons and neutrons. Leptons are loners that never do. No known particle directly links the two families. A leptoquark would break that separation. It is a hypothetical particle that couples directly to a quark and a lepton at the same time, a bridge between the two families that the rulebook keeps apart. Because a leptoquark touches both a quark and a lepton in a single interaction, it can reach straight into our decay. Picture the bottom quark decaying, and instead of going the long way around through the ordinary penguin loop, it briefly exchanges a leptoquark, which ties the quarks and the muons together directly. This opens a new path for the decay, one that the standard model does not have. And crucially, if the leptoquark couples more strongly to muons than to electrons, that new path would affect muon decays and leave electron decays alone, shifting R of k below 1 and turning the ninth dial exactly as the data seem to want. You can think of a leptoquark as a secret door between two rooms that were supposed to have no connection. In the rulebook's house, the quark room and the lepton room share no doorway. To get from one to the other, you have to go the long way, through the hall of the ordinary forces. A leptoquark punches a private door straight through the wall. Once that door exists, traffic can flow between the rooms in ways the original blueprint never allowed, and the decay rates shift accordingly. Leptoquarks are not a desperate invention conjured only to explain these anomalies, and that is part of their appeal. They appear naturally in several ambitious theories that try to unify the forces, the so-called grand unified theories, which seek to show that the strong, weak and electromagnetic forces are three faces of one deeper force. In many such theories, quarks and leptons are placed into the same larger family, and leptoquarks emerge as a consequence, the particles that mediate transformations within that unified family. So a leptoquark would not only patch the anomalies, it might be a signpost toward a much grander structure beneath the rulebook. There is a further reason theorists were drawn to leptoquarks, and it points ahead to something we have not yet fully met. A well-chosen leptoquark could explain more than just the bottom to strange muon anomalies. The same particle, with the right properties, might also account for a separate set of anomalies involving the tau lepton in a different family of B-meson decays, and even, in some versions, the puzzle of the muon's magnetism. One particle, potentially resolving several distinct cracks at once. That kind of economy is exactly what physicists find beautiful and hard to resist, because nature has often rewarded the search for a single cause behind many effects. But a leptoquark is a strong claim, a genuinely new kind of particle unlike anything yet seen, and it would have consequences elsewhere. If leptoquarks exist and are light enough, the great detectors at the Large Hadron Collider should be able to produce them directly and see them, and searches for exactly that have been carried out. So far, those direct searches have come up empty, which pushes any leptoquark to be quite heavy, though not so heavy that it could not still do the job through virtual loops. The leptoquark is the bolder of the two main candidates. The second is more conservative, a new force carrier in the same mould as ones we already know, differing mainly in that it would play favourites. The second candidate keeps closer to familiar ground. Recall the Z, the neutral messenger of the weak force, the one that touches a particle and hands it back unchanged. Now imagine a heavier sibling of the Z, a new neutral force carrier much like it, but with its own quirks. Physicists call this hypothetical particle a Z prime, the prime marking it as a cousin of the original. Where a leptoquark is a strange new bridge between quarks and leptons, a Z prime is a more conventional idea, simply another force carrier of a kind we already understand added to the roster. The key twist that would let a Z prime explain the anomalies is that, unlike the ordinary Z, it would not treat all the lepton flavors the same. It would couple more strongly to muons than to electrons. That single feature is enough. A Z prime that favors muons would open a new contribution to the bottom to strange decay whenever muons are involved, shifting the muon rates and leaving the electron rates untouched, exactly the pattern the measurements traced. It would turn the ninth dial by adding a new muon-specific path to the decay. A Z prime that plays favourites among the generations is not as strange as it might first sound. The standard model's own forces treat the generations alike, yes, but there is no iron law forbidding a new force from distinguishing between them. Many proposed extensions of the rulebook include new force carriers tied specifically to certain generations, and a muon-preferring Z prime sits comfortably among them. It would be a new fundamental force, feeble and carried by a heavy messenger, that simply happens to care which lepton sibling it is dealing with. Think of the ordinary Z as a public bus that any passenger can board on equal terms, no matter who they are. A Z prime that favours muons would be like a second, private shuttle that only certain passengers can use, running a route the public bus does not. Add that shuttle to the transit system, and the travel patterns of those particular passengers change, while everyone else's stay the same. The muons get a new way to get around. The electrons are left with the old routes. That selective new option is precisely what would tilt R of K away from 1. Between the leptoquark and the Z prime, physicists had two concrete, testable pictures of what might lie behind the anomalies, and the two make different predictions elsewhere. A leptoquark, being a bridge between quarks and leptons, tends to leave certain distinctive fingerprints, and can more easily tie together anomalies in different decay families. A Z prime, being a force carrier, would show up in other ways, for instance by subtly affecting how B mesons and their antimatter twins turn into one another, a process the Z prime could nudge. So the two candidates were not just names, they were rival hypotheses, each with its own web of consequences that further measurements could confirm or rule out. This is science working as it should. Faced with an anomaly, theorists did not simply declare victory. They built specific models, worked out what each would imply across many different measurements, and handed the experimenters a list of places to look. If a leptoquark were real, certain other things should be seen. If a Z prime were real, a different set. And if neither showed up anywhere else while the anomalies faded, that too would be an answer, pointing back toward ordinary physics misunderstood. For a while, one particular reason to favour these bold explanations came from an entirely separate family of decays, ones involving not the muon but its heavier sibling, the tau. And unlike the muon and electron ratios, that tau anomaly has proven remarkably stubborn. Until now, every crack we have examined lived in the same kind of decay, a bottom quark turning into a strange quark through a rare loop, with muons or electrons coming out. But there is a second, quite different family of B-meson decays that developed anomalies of its own, and this one involves the heaviest lepton, the tau. Understanding it doubles the intrigue, because it is a completely separate process pointing, perhaps, in a related direction. In these decays, a bottom quark does not turn into a strange quark, it turns into a charm quark, and it does so by the ordinary charged route, emitting a W that then becomes a lepton and its matching neutrino. This is not a rare loop decay. It is a common, direct, tree-level decay, one of the most frequent ways a B-meson falls apart. The lepton that comes out can be an electron, a muon, or a tau, and once again lepton flavor universality makes a firm prediction about the proportions, after accounting honestly for the tau's much larger mass. Physicists measure this with ratios too, called R of D and R of D star, where the D refers to the charmed particle produced in the decay. Each ratio compares how often the decay produces a tau against how often it produces the lighter leptons. The rulebook, correcting carefully for the heavy tau, predicts specific values, and the measurements have come in consistently high. The decays produce taus somewhat more often than the standard model says they should, as if the tau were being favoured, as if the weak force reached for the heavier sibling a little too eagerly. This anomaly was seen first at the Babar experiment in California, then confirmed at the Belle experiment in Japan, and later added to by LHCb in Europe and by Belle's successor, Belle Two. 4 different experiments using different machines and different techniques all found the tau appearing more often than predicted. Combining their results, the world average for these ratios sits above the standard model prediction by close to 4 sigma. That is firmly in the territory of strong evidence, short of the 5 sigma discovery line but well beyond a passing curiosity. What makes this tau anomaly so compelling alongside the muon ones is the possibility that they share a root. The muon anomalies suggested muons being treated unusually in one family of decays. The tau anomalies suggest taus being treated unusually in another. Both are violations of the same principle of lepton fairness, just involving different siblings and different processes. A single new particle, a well-chosen leptoquark in particular, could in principle touch both, favouring taus in the charged decays and muons in the loop decays. The dream was that these were not 2 anomalies but one, glimpsed from 2 directions. There is a further reason the tau anomaly carries weight, and it is worth stating plainly. Because it happens through the common, direct route rather than a rare loop, its prediction is comparatively clean. The tree-level decay is less shrouded in the hardest strong force uncertainties than the delicate penguin decays are, and by taking ratios of tau to lighter leptons, much of the remaining strong force messiness cancels, just as it did for R of K. So R of D and R of D star are among the more trustworthy anomalies in the whole collection, less easily blamed on a calculation gone wrong. That trustworthiness is exactly why this particular crack deserves its own close look. Of all the hints gathered over the past decade, this is the one that has best withstood the arrival of more data. While other anomalies wavered, the tau excess held its ground, and understanding why it has been so stubborn is the next piece of the picture. It is worth pausing on why the tau anomaly has endured while others softened, because endurance under scrutiny is the rarest and most valuable quality an anomaly can have. Most hints in particle physics erode as more data comes in. The tau excess, remarkably, has not. Across more than a decade, as each experiment added measurements and refined its methods, the ratios R of D and R of D star kept landing above the prediction, and the combined significance held near 4 sigma rather than melting away. Part of the reason is the one we just met. The decay is direct and comparatively clean to predict, so the anomaly cannot be easily dismissed as a strong force calculation gone astray. But there is more to it than that. The measurement of a tau is genuinely difficult, because the tau, being heavy, itself decays almost immediately into other particles, including at least one neutrino that escapes undetected. A neutrino carries away energy you can never measure, which blurs the reconstruction of the original decay. Different experiments handle this blurring in different ways, using different techniques to infer the tau's presence. That variety is exactly what makes the persistence impressive. If a single experiment, using a single method, kept seeing an excess, you might worry that some flaw in that one method was manufacturing it. But here you have several experiments, on different continents, producing B mesons in different ways, catching the elusive tau through different strategies, and all of them land above the prediction. For a false effect to survive that gauntlet, it would have to fool many independent methods in the same direction, which is far harder to arrange by accident than fooling one. Picture several different survey teams, each using its own instruments and its own procedures, sent independently to measure the height of the same distant mountain. If one team reports the mountain is taller than the map says, you might suspect a faulty instrument. If every team, with different instruments and different methods, independently reports the mountain taller than the map, you begin to think the map is wrong. The tau anomaly is that mountain, measured too tall by too many independent teams to shrug off easily. Still, honesty requires holding the caution firmly even here. 4 sigma is strong evidence, but it is not discovery, and the field has watched 4 sigma effects fade before. The measurement remains hard, the escaping neutrinos remain a challenge, and it is not impossible that some shared subtlety in how the experiments model these decays could be pulling them all the same way. The value of more data is precisely that it can push a genuine 4 sigma effect toward the decisive 5, or reveal it slipping back toward the prediction. Until that happens, the tau excess is a very good reason to keep looking, not yet a reason to declare that the rulebook is broken. What the tau anomaly did, at the height of the excitement, was strengthen the sense that something coherent might be going on. Here were 2 families of anomalies, the muon ones in the loop decays and the tau ones in the direct decays, both bending the same rule of Lepton fairness, and both potentially explained by the same kind of new particle. The whole seemed larger than the sum of its parts. A single missing page in the rulebook might account for all of it. And there was one more thread, older than any of these and famous in its own right, that many hoped belonged to the same tapestry. It concerned not how the muon decays, but how it spins in a magnetic field, a tiny wobble that had been teasing physicists for decades. Set a spinning electric charge in a magnetic field, and it behaves like a tiny compass needle, twisting to align with the field. Every charged particle with spin has this magnetic character, and its strength is captured by a number physicist called G. When Paul Dirac wrote down his famous equation for the electron in 1928, marrying quantum mechanics to relativity, it made a clean and startling prediction. For a fundamental particle like the electron, G should equal exactly 2. No adjustment, no decoration, just 2. It was one of the early triumphs of the theory. But that clean value of 2 was not quite the final word, and the reason reaches back to the churning vacuum we met earlier. A real particle is never truly alone. It is constantly emitting and reabsorbing virtual particles, dressing itself in a cloud of fleeting borrowings from empty space. Those virtual companions slightly alter how the particle responds to a magnetic field, nudging G just above 2. The small excess beyond 2 is what physicists call the anomalous magnetic moment, and it goes by the shorthand G-2. In 1948, the physicist Julian Schwinger calculated the first and largest piece of this correction, arising from the particle briefly emitting and reabsorbing a single virtual photon. His result was a specific small number, a shift of about 1 part in 800 added to G. The calculation was so elegant and so important that the formula is carved on his headstone. It was a landmark because it showed that the tiny deviation of G from 2 could be computed from theory and checked against experiment, turning G-2 into one of the most precise meeting points of prediction and measurement in all of science. Here is why this matters for our story. That cloud of virtual particles dressing the muon includes, in principle, every particle that exists, even ones we have not discovered. Each virtual visitor contributes its own small piece to G-2. So an exquisitely precise measurement of the muons G-2 compared against an exquisitely precise prediction becomes another remote sensor for unknown particles, exactly like the rare decays. If there is a new particle out there coupling to muons, it should join the virtual cloud and shift G-2 by a tiny calculable amount. Measure the wobble precisely enough, and you might feel the new particle's presence in it. The muon is a far better probe for this than the electron, and the reason is its greater mass. A heavier particle is more sensitive to the effects of other heavy particles in its virtual cloud, so any new physics would show up more strongly in the muons G-2 than in the electrons. This is why, for decades, the muon's magnetic moment has been a prize target, measured and predicted with ever-increasing care, each side racing to pin down more digits and see whether they still agree. And for a long time, they seemed not to agree. Measurements of the muons G-2, first at the Brookhaven laboratory and later, more precisely, at Fermilab, came in a little above the theoretical prediction that physicists had settled on. The gap was small but persistent, hovering around 3 to 4 sigma, and it fit the dream perfectly. A muon behaving as if dressed by some extra virtual particle, a muon touched by new physics, right alongside the muon anomalies in the B meson decays. For years, many hoped these were all the same story, a single new muon-loving particle showing its face in decay after decay and in the muon's very spin. That hope led to one of the most ambitious precision experiments ever mounted, built around a single enormous magnetic ring, and its results would sharpen the puzzle to its finest point. The experiment lived inside a magnificent object, a circular magnet 15 meters across, storing muons as they raced around its ring. The story of that ring is itself remarkable. It was originally built at the Brookhaven laboratory on Long Island, and when the work moved to Fermilab near Chicago, the fragile 50-ton ring had to be transported whole, unable to be taken apart. It travelled by barge down the East Coast, around Florida, up a river, and finally overland. A giant white circle inching along highways at night while crowds came out to watch. It arrived intact, was installed, and went to work. The principle of the measurement is beautiful. Muons are injected into the ring and circle within the powerful magnetic field. As they go, their spins, those tiny compass needles, wobble, and the rate of that wobble depends directly on G-2. Because muons are unstable, each one eventually decays, and the direction its decay products fly reveals which way its spin was pointing at that instant. By catching millions upon millions of these decays around the ring, physicists reconstruct the exact rate of the spin's wobble, and from it extract G-2 to astonishing precision. Fermilab announced results in stages. A first result in 2021 confirmed the earlier Brookhaven measurement and strengthened the apparent gap with theory. Further results followed as more data was analysed, each tightening the precision. Then, on the 3rd of June 2025, the collaboration announced its final result, combining all 6 years of data into the most precise measurement of the muon's magnetic moment ever made, pinning it down to a precision of around 120 parts per billion. As a feat of experimental physics, it was a triumph, a number measured with breathtaking care and confirmed across years of running. The experimental value was rock solid. The muon's wobble had been measured about as well as anyone could hope to measure it, and the measurement was stable, agreeing with itself across every stage. If the story were only about the experiment, it would be a clean tale of ever sharper measurement converging on a firm number. The drama, it turned out, was not on the experimental side at all. It was on the side of the prediction, in the fiendishly hard task of calculating what the standard model actually says G-2 should be. Because to claim new physics, you need two things measured precisely: the experimental value and the theoretical prediction. A gap between them only means something if you trust both. The experiment had done its part beautifully. but the prediction depended once again on the hardest part of the whole rulebook to compute, the contribution of the strong force of virtual quarks and gluons swirling in the muon's cloud. And it was there, in the theory, that the ground began to shift beneath the Anomalies' feet. The strong force piece of G-2 is called the hadronic contribution, and it is notoriously difficult to pin down. For years it was estimated using one particular method, drawing on experimental data from other collisions. That method gave a prediction which sat below the measured value, producing the celebrated gap. But a second method of computing that same strong force piece was maturing, and as it sharpened, it began to tell a different and unsettling story. The second method is called lattice quantum chromodynamics, or lattice QCD, and it takes a brute force approach to the hardest calculation in the rulebook. The strong force, described by the theory called quantum chromodynamics, cannot be solved with pen and paper for these purposes. So instead, physicists lay down a grid, a lattice, of points in space and time, and simulate the churning of quarks and gluons directly on that grid using enormous supercomputers. Refine the grid, add computing power, and the answer sharpens. For the muons G-2, lattice QCD offered an independent way to compute the troublesome strong force contribution from first principles, without relying on the other experimental data. For years, the lattice approach was not precise enough to settle anything, but it improved steadily, and around 2020 a major lattice calculation delivered a result precise enough to matter, with a startling implication. Its value for the strong force contribution was larger than the older data-driven method had found, and a larger strong force contribution meant a larger predicted G-2, one that sat much closer to the measured value. If the lattice result was right, the famous gap between prediction and measurement shrank dramatically, and the anomaly, the hint of new physics in the muon's wobble, largely dissolved. This split the field into a genuine and uncomfortable puzzle. Two ways of computing the same strong force contribution disagreed with each other. The older data-driven method gave a prediction well below the measurement, keeping the anomaly alive. The newer lattice method gave a prediction much closer to the measurement, killing it. The two methods were not both able to be right. The disagreement between the predictions had become larger, in a sense, than the original disagreement between prediction and experiment. The puzzle was no longer only about muons and magnets. It was about which calculation to trust. To settle it, physicists formed an international effort, the muon G-2 theory initiative, gathering the experts to hammer out an agreed prediction. Their first assessment, published in 2020, leaned on the data-driven method and preserved the anomaly. But as the lattice results were confirmed by more groups, and as tensions emerged in the old experimental input data itself, the picture changed. When the initiative published an updated prediction in 2025, it rested primarily on the lattice calculations, and the new predicted value moved up, into agreement with the measured wobble. By this reckoning, the muon's magnetic moment no longer disagreed with the standard model at all. There was a further wrinkle sharpening the confusion, worth naming because it lies at the heart of the matter. The old data-driven method relied on measurements of a particular kind of collision, electrons meeting their antimatter partners to produce hadrons. A newer such measurement, from an experiment called CMD3, came in notably different from the older ones it was meant to confirm. That discrepancy in the input data undermined confidence in the data-driven prediction and helped tip the balance toward the lattice results. The anomaly was not so much disproven as dissolved into a thicket of disagreeing measurements and methods. So the muon's wobble, which for years stood as one of the strongest hints of new physics, and a pillar of the hope that a muon-loving particle was out there, has been severely undermined, though not with absolute finality. The experiment is beautiful and firm. The prediction has shifted toward the experiment and by the current best reckoning now matches it. The pillar did not so much fall as quietly turn to sand, and it was not the only hint from this whole saga to weaken. The cleanest anomaly of all, the one this story was built around, took its own hard turn. Return now to R of k, the clean ratio of muon decays to electron decays that opened this whole modern chapter. For years it sat below 1, the sharpest and most trusted of all the anomalies, the one whose prediction was so clean that a deviation seemed almost impossible to blame on faulty calculation. It was the flagship. If any of the hints was going to become a discovery, many expected it to be this one, and then, in December of 2022, LHCb delivered an updated measurement, and the flagship changed course. The new analysis used more data and, crucially, a far more careful treatment of the ways the detector handles electrons and muons differently. Recall that this had always been the hardest part of the measurement. Electrons are messier to catch than muons, prone to radiating away energy, and any imperfect correction for that difference could create a false gap or hide a real one. The updated analysis dug into these effects with much greater rigour, identifying backgrounds and detector subtleties that the earlier work had not fully accounted for, and when the dust settled, the new value of R of k came out consistent with 1. The anomaly in this cleanest of channels was gone. Muons and electrons, it now appeared, were being produced in the proportion the rulebook demanded after all. The earlier low values had not been a new particle whispering through the decay. They had been, in large part, an underestimate of how differently the detector treated the two kinds of leptons. When that difference was handled correctly, the gap closed. The flagship anomaly had sailed back to the standard model. This was a hard moment, and it is a deeply honest one that many popular tellings of this story never got around to including, because the exciting videos were made when the anomaly still stood. It is worth sitting with what it teaches. The measurement that seemed cleanest, least vulnerable to calculation errors, most likely to survive, was the one that reversed. The trouble was not in the theory's hard calculations, as the cautious had worried about for the messier anomalies. It was in the experiment itself, in the brutal difficulty of comparing two kinds of leptons caught by two different systems. The universe had sent another pair of standard model socks. Picture a detective who has built a case around one especially strong piece of evidence, a clear fingerprint at the scene. Then the lab revisits the print with better tools and finds it was smudged, that the match was an artifact of the earlier analysis. The case does not necessarily collapse, but its centerpiece is gone, and everything else must now be weighed without it. That is what the 2022 R of K result did to the muon anomalies. It removed the piece of evidence that had felt most secure. It is important to be precise about what this reversal did and did not do. It did not erase every anomaly. The tau excess in the other family of decays, R of D and R of D star, still stood near 4 sigma, untouched by this, and some of the muon rate and angular measurements still sat below their predictions. But the cleanest pillar, the muon to electron ratio, no longer showed a violation of lepton fairness. The strongest and most trusted evidence for the specific idea that muons and electrons are treated differently had faded back into agreement. Between this and the softening of the muons G-2, two of the load-bearing pillars of the grand unified hope had weakened badly in just a few years. But there was a deeper lesson threaded through all of it, one about how the rulebook can fool us even when no experiment is at fault, hiding in the parts of the theory we compute least well. Step back from any single result and consider the pattern of how these anomalies weakened, because there is a lesson in it that reaches beyond this one story. Again and again, the vulnerability lay not in whether new physics existed, but in the boundary between what the standard model cleanly predicts and what it predicts only murkily. The murk has a source, and it is almost always the same one: the strong force and the fiendish difficulty of calculating what it does inside these decays. The specific culprit in the muon decays has a name. It is called the charm loop, or more broadly, long-distance hadronic effects. Recall that these decays proceed through loops in which virtual particles flicker in and out. Among those virtual visitors are charm quarks, and charm quarks, feeling the strong force, can do complicated things. They can briefly form fleeting bound states, resonances, that influence the decay in ways that are genuinely hard to compute from first principles. These charm loop effects contribute to the very same quantities the anomalies showed up in, including the 9th Wilson coefficient that the global fit wanted to shift. Here is the uncomfortable heart of it. A charm loop effect, if it is larger than physicists assumed, would shift that 9th dial in exactly the same direction that a new particle would. From the data alone, a genuine new particle and an underestimated charm loop can look identical. Both turn the same knob the same way, so a deviation in the muon rates or in P5' might be a message from beyond the rulebook, or it might be the rulebook itself speaking through a part of the strong force we did not calculate well enough. The signal of new physics and the shadow of hard-to-compute known physics wear the same face. Think of hearing a faint knocking in your house at night and becoming convinced someone is at the door. It could be a visitor, something genuinely new arriving, or it could be the ordinary house itself, a pipe settling, a branch on the window, a sound the building always could make but that you had not learned to recognize. Before you throw open the door announcing a guest, you have to rule out the house. In these decays, the charm loop is the house, the familiar structure making a sound that mimics a knock, and ruling it out is painfully difficult. This is why the clean measurements mattered so much, and why the reversal of R of k stung so deeply. R of k was supposed to be immune to the house, because taking the muon to electron ratio divided away the strong force effects, charm loops included. Whatever the charm quarks did, they did to both muons and electrons alike, so they should have cancelled in the ratio. That immunity was the whole reason R of k was the flagship. When even that measurement reversed, it turned out the trouble there was a different one, in the detector rather than the theory. But the episode still drove home how many ways a hint can arise that has nothing to do with new particles. The honest summary is this: the Messier anomalies, the rates and the angles could plausibly be charm loops rather than new physics, and no one has been able to prove otherwise. The cleanest anomaly, which charm loops could not have faked, went away for a different reason entirely. And the muon's magnetic moment, once a separate pillar, was undermined by a disagreement over how to compute yet another piece of strong force physics. The strong force, the hardest thing in the rulebook to calculate, sits behind nearly every place where hope has dimmed. And yet, after all these reversals and complications, the story is not over, and the anomalies have not all vanished. Something is still standing, and it is worth taking careful stock of exactly what. So let us take honest stock, laying out what has fallen and what remains, because the truth of where this stands is more interesting than either a triumphant or a dismissive telling. 3 great strands of evidence once wove together into the hope of a single new muon-loving particle. 2 of those strands have badly frayed, 1 remains surprisingly intact, and a scatter of smaller hints persists in an ambiguous middle. The first strand to fray was the muon's magnetic moment, the G-2 anomaly. Once a 3 to 4 sigma gap that fit the dream perfectly, it has been undermined by the shift in the theoretical prediction toward the measured value, driven by lattice calculations and by trouble in the old input data. By the current best reckoning, the muon's wobble agrees with the standard model. It is not 100% settled, since the disagreement between calculation methods is still being resolved, but as evidence for new physics it has gone quiet. The second strand to fray was the flagship itself, R of k, the clean muon to electron ratio. Its reversal in 2022, once the detector effects were handled properly, brought it into agreement with 1. The sharpest, most trusted sign that muons and electrons were treated differently faded back to fairness. With it went much of the direct evidence for the specific violation of Lepton universality between the 2 lighter siblings. But the third strand still stands, and it is the tau anomaly, R of d and R of d star. The excess of taus in the charge current B meson decays has held near 4 sigma across 4 experiments and more than a decade of data. It is comparatively clean to predict, measured by independent methods that all agree, and it has not faded as the others did. Of all the cracks in the rulebook this story has examined, This is the one that remains genuinely open and genuinely intriguing. Something may still be favouring the heaviest lepton in a way the standard model does not explain, and in the ambiguous middle sit the muon rate measurements and the angular quantities like P5'. Several of these still come in somewhat below or away from their predictions, but these are precisely the measurements shadowed by the charm loop, the ones where hard to calculate strong force effects could mimic a new physics signal, so they linger as unresolved hints, neither confirmed as new physics nor cleanly explained away, waiting on better calculations and more data to tip them one way or the other. The picture, then, is neither the discovery some hoped for nor the empty flukes a cynic might claim. It is a genuine unresolved situation, with one solid surviving anomaly, a cloud of ambiguous ones, and two former pillars that have weakened. This is what real physics at the edge looks like most of the time. Not a clean triumph and not a clean failure, but a stubborn, honest uncertainty that only more evidence can settle. It would be easy, standing here, to feel let down, as though the excitement of the past decade led nowhere. That would be the wrong lesson. Each reversal taught something real, how detector effects can masquerade as new physics, how the choice of calculation method can make or break an anomaly, how the strong force hides signals and fakes them. The field is far wiser about these decays than it was 10 years ago, and the surviving tau anomaly, together with the lingering muon hints, means the question this whole story asked is still genuinely, cautiously open. Which raises the practical question of how it actually gets answered from here, because these things do get answered, in time, and the machinery to answer this one is already running. The way this ends is not with argument, but with data, and a great deal of it is already on its way. The Large Hadron Collider has been running a new campaign, called Run 3, and the LHCb detector was substantially upgraded before it began, rebuilt to collect data far faster than before. Over the next several years, it is expected to gather several times more of these B-meson decays than it had in all its previous running combined. More decays means smaller uncertainties, and smaller uncertainties are exactly what is needed to turn an ambiguous hint into a clear yes or no. On the other side of the world, the Belle Two experiment in Japan is doing complementary work. It produces B-mesons in the cleaner environment of electron-positron collisions, which makes certain measurements, particularly the difficult tau ones, more tractable. Belle Two is accumulating its own large data set, and its measurements of R of D and R of D star will either reinforce the surviving tau anomaly or begin to erode it. Because Belle Two and LHCb catch these decays in different ways, their agreement or disagreement carries real weight. A hint that survives in both is far harder to dismiss than one seen by a single machine. The arithmetic of significance tells you what to watch for. The tau anomaly currently sits near 4 sigma. If its central value holds steady as the data pile up, the shrinking uncertainties will push it past 5 sigma into discovery territory, and the field will have found a genuine violation of Lepton fairness. If instead the central value drifts back toward the prediction, as more decays are counted, the anomaly will fade the way R of K did, and the tau excess will join the list of hints that dissolved. There is no third option that stays interesting. More data forces the question closed. For the muon rate and angular anomalies, the path is harder, because their resolution depends not only on more data, but on better calculations of those troublesome charm loop effects. Progress there is being made on 2 fronts at once: experimenters gathering more decays to sharpen the measurements, and theorists working to pin down the strong force contributions, sometimes by measuring related processes that constrain the charm loops directly. Only when both improve together can these ambiguous hints be cleanly sorted into new physics or ordinary physics misunderstood, and the direct searches continue in parallel. If a leptoquark or a Z' is really behind any surviving anomaly, and if it is light enough, the great general-purpose detectors at the Large Hadron Collider might produce it outright and see it plainly. So far they have not, which steadily tightens the noose on how light such a particle could be. A discovery in the rare decays and a direct sighting of the culprit would together make an airtight case. A persistent anomaly with no particle ever found directly would be a genuine puzzle demanding explanation. What all this means is that the story you have followed tonight is not a finished one. It is a live investigation, with new results arriving year by year, each one nudging the picture toward resolution. Within this decade, the Tau anomaly in particular is likely to be settled decisively, one way or the other. The machinery is built, the data is accumulating, and the question of whether nature truly plays favourites among the Leptons is being answered in real time, in tunnels beneath Europe and Japan, one counted decay at a time. So we return, at the last, to the simple question we started with, the one about a particle falling apart and whether nature plays fair, and we can now give it the honest, careful answer it deserves. We began with muons falling silently through your body, and with a promise buried in the fact that the electron, the muon, and the tau seem to be exact copies of one another, differing only in their weight. The promise was fairness, the principle that the forces of nature treat these three siblings identically, and the question we set out to follow was whether that promise is truly kept, or whether deep in the way particles fall apart, nature quietly plays favourites. Here is the honest answer, in the plainest words. As of now, we do not know, and that not knowing is real and specific rather than vague. For years, a cluster of hints suggested the promise might be broken, that muons in particular were being treated differently in the rare decays of bottom quarks, and that the muon's very spin carried a trace of something new. Two of the strongest of those hints have since weakened badly. The cleanest measurement of muon versus electron fairness returned to agreement once the experiment was done more carefully. The muon's magnetic wobble came back into line once the theory was computed a better way. Those two retreats are the sound of the standard model, once again, proving tougher than its challengers hoped. But one strand still stands, and it stands stubbornly. In a different family of decays, the heaviest lepton, the tau, keeps appearing more often than the rulebook says it should, and this excess has survived 4 experiments and more than a decade of scrutiny at close to 4 sigma. It is the one place where the promise of fairness still looks, honestly, as though it might be broken. Alongside it linger a handful of muon rate and angular hints, real but ambiguous, shadowed by strong force effects we cannot yet calculate cleanly enough to trust. That is the true state of things, not a discovery, not nothing, but a genuine open question with one good surviving lead. What would it mean if that lead holds, if the tau excess crosses 5 sigma in the coming years? It would mean the rulebook has a page missing. It would mean there is a new particle in nature, a leptoquark bridging quarks and leptons, or a new force carrier that plays favourites, reaching into these decays and tipping the balance. It would be the first crack in the standard model found not by brute energy, but by patient counting, a signpost pointing toward whatever deeper theory lies beneath the one we have. After half a century of the rulebook passing every test, that would be enormous, the beginning of physics beyond the map's edge. And if the lead fades, as the others did, then the standard model will have withstood one more determined assault, and we will understand these decays and the strong force that muddies them better than we ever did. Even a fading anomaly leaves the field wiser. Either way, the counting continues and the answer comes. There is something worth carrying away from all of this, beyond the particular fate of any one measurement. It is a picture of how honestly this work is done. Nature does not hand over its secrets to enthusiasm. It yields them only to careful, patient, self-doubting effort, to thousands of people cross-checking each other, to the willingness to watch a beloved anomaly dissolve and report it plainly. The muons still fall through you as they always did, indifferent to our hopes, obeying whatever the true rules are. Our task is only to listen closely enough and count carefully enough to find out what those rules really say. And right now, in the quiet bookkeeping of how particles die, we are still listening for the answer to a very old and simple question. When a particle falls apart, does nature really play fair?